Welcome. This is lecture 44, and in this thing we prove the following theorem. R Noetherian, then dimension of Rx is equal to dimension of R plus 1. So as a corollary, we would then immediately see that dimension of K, x1 through xn, is n, where K is a field. Okay. This is a statement that we had wanted to prove a little while ago, but we needed this statement, that the theorem for which we will need to use things that we learned so far. Okay. We needed to use principal ideal theorem and its consequences. So we didn't need to develop the dimension theorem in the way that we have done, but this is one way of proving it. So first, before we go to the theorem, let's start with some easy propositions. We will prove the theorem at the end. Dimension of Rx, even if R is any ring, not necessarily Noetherian, any commutative ring, okay, then dimension of Rx is at least, is bigger than dimension of R. Why is that? Proof. Let P0 PL be a chain in R, chain of primes in R. Okay. Then it's easy to check that P0 extended to Rx, PL extended to Rx. Okay. So Rx modulo this. Okay. So Rx modulo this ideal would be R modulo P0 adjoint X, or one can prove that they're isomorphic. So R mod P is a domain, therefore R mod P adjoint X is a domain. Therefore, Rx mod P Rx is also a domain. Okay, so this is a prime ideal. And after this prime ideal, we can put at least one more, which is take this and the variable x. Okay. So Rx modulo this prime ideal is just R mod P. So it's a domain. Okay. So this is a chain of primes in Rx. Okay, so for every chain there's a chain of length at least one more. So therefore, dimension of Rx is bigger than or equal to, is bigger than dimension of R. Okay, so this is the general situation. Okay, so we need one more lemma about let Q1 inside Q2 could be equal also, Q2 be prime ideals of Rx, such that when we contract them to R, we get the same prime ideal of R. So it is possible. For example, we could take R could be a field, and then Rx is a PID, and if you take any irreducible polynomial, when you contract, so that's a non-zero ideal in Kx, in Rx, when you contract it, you just get 0 because K is a field. Okay, so, but of course a zero ideal of Kx also contracts to 0. So it is possible that there is a pair of ideals with this containment with this property. This is not unusual. Then the smaller one, Q1, is the extended ideal. This is a prime, its extended ideal is also a prime in this case. Extending to polynomials is still prime. So if you have a pair like this, then the smaller one, if you have a pair with this property, then the smaller one is the extended ideal. Okay, proof. Let P be this Q1 contracted to R, which is also Q2 contracted to R. Now, if we go modulo P, then, okay, so then R mod P, we can look at it this way. Okay. Inside here is Q2, okay, Q2 bar, Q2 mod P Rx. So this is, remember, it's Rx mod P Rx. Okay. So Q2 mod P Rx, that contains Q1 mod P Rx. Okay. And here this contracts to 0, and both of them contract to 0. Both of them contract to 0 here. That's the picture. But this is a domain. So invert every non-zero element of R mod P. Okay. So we get a fraction field of R mod P. So we get, so we do this R mod P in R mod P and R mod P adjoint X. Okay. If you invert non-zero elements inside here, they don't intersect Q2 and Q1, the images of Q2 and Q1. Okay. So notice that no element of, anyway, we just have to worry about Q2 because that's the bigger one. No element of Q2 is inverted. Because Q2, I mean, this thing contracted to R is just 0. Contracted to R mod P is just 0. So nothing has been inverted in Q2. Okay. We are only inverting elements of R, but on both sides. Okay. So in other words, so then we get K, which is a field. So this is the fraction field. K to K adjoint X. Okay. And then we have some, let's just use a slightly different symbol, Q2 and Q1, both of them contracting to 0 here. This is a fraction field, okay, and there is a containment like this. Okay. But then it is, but this is a PID. Sorry, I did, where did I say? I'm sorry, one, it has to be equal. This must be strictly smaller. Sorry, all these containments were strictly smaller. Okay, so this Q2 inside Q1, okay, any will also be like this. Okay. And but this is a PID. If you have two prime ideals in a PID, then the smaller one must be 0. So this one says that Q1 is 0. But then when we work backwards, this just says that Q1 is PRX. Okay, so this is the proof. And as an immediate corollary, we can get the following, which is still not good enough for us. Okay. That's because if you take any chain, okay, so proof. If we take Q0 inside Q1, QL, so this will give a chain, if you contract them, chain of length greater than or equal to L minus 1 divided by 2. Because three things in this together cannot contract to something, I mean, if three distinct things in a chain cannot contract to the same P below, the previous one says only two of them can, and that's what we get. Okay, so this is in the generality of arbitrary commutative rings, this is all that one can say. So now we go back to this theorem. If R is Noetherian, then dimension of Rx is 1 more than dimension of R. Okay, and as an immediate thing, we see this corollary. Okay, so proof of, now we can just prove the theorem. Proof of theorem. Okay. So we take a prime in Rx. Prime. And P is the contraction of that prime ideal into R. Okay. So what we want to show is that height of Q is less than or equal to height of P plus 1. If we show this, then, well, if we take any chain, then its supremum length will be less than the supremum of these such things plus 1. But then supremum of such things is dimension of R. Okay, so we will get a less than or dimension is less than or equal to 1. Dimension of Rx is less than or equal to maybe one should just write. Let me just write this thing. So what? Okay, okay, suppose we prove this. Okay. Then for every chain Q0 inside Q1 inside QL of primes in Rx, okay, we get a chain of length greater than or equal to L minus 1 in spec S. Okay. So therefore, we take supremum of such L, then here we will get supremum of such L minus 1. So from this we would get that dimension of Rx is less than or equal to dimension of R plus 1. The other inequality has already been established. Okay. So therefore, we want to show this. So that's okay. So we are discussing something about height of some two primes Q and P, and to determine this we need to worry only about primes inside P. So we could just localize inside, in R we could just invert everything outside P and do the same thing in Rx, just invert everything outside P. Okay. So replace R by R localized at P and Rx by R localized at Px, which is also the same thing as R minus P inverted inside Rx. Okay. To assume that R is a local ring and Q contracts to the maximal ideal. Okay, so this is the reduction that we have done. Okay, and we want to show that height of Q is less than or equal to dimension of R plus 1. Okay, that's how we just translated this thing. Okay, so now we induct on dimension of R. Dimension of R is 0. Okay. Then Q contracted to R is M. Okay. What about the height of? Okay. So now let's look at. So now we want to argue that height of MRX is 0. Why? If not, there exists some P, there exists some Q prime inside MR, strictly inside MRX. Right? This is not a minimal prime inside Rx. It is a prime. What we are claiming that it's not a minimal prime inside Rx. But what can this contract to? Well, it has to contract to a maximal, to a prime ideal, but there's only one, in this assumption there's only one prime ideal in R, so this must be equal to M. But this contradicts the lemma that if you have a chain of, if you have primes like this, then well, this does not need the lemma, sorry. This like this, then Q prime, I mean, under this condition, okay, so this says that Q prime will contain MRX. Sorry, this does not need the lemma, it's just QRX, and this is a contradiction because we just said that it's a proper subset of Rx. I mean, any ideal contains the extension of its contraction. So this is just, okay. So therefore, that proves the statement. That has been, I mean, because of this, that has been established. Okay, so now let's look at height of Q. Okay, so Q of course contains MRX. Okay. Q contains MRX. Okay. Suppose there is a Q tilde here. That okay, but then all three of them will contract to MRX. This will imply that Q contracted to R is Q tilde contracted to R, which is equal to MRX contracted to R, which is M. Three distinct things in a chain contracting to the same prime ideal contradicts the lemma. Okay. Therefore, there does not exist any Q tilde prime. Sorry, by this I didn't write it, but by this I meant prime. Okay. Prime such that Q contracts to such that Q properly contains Q tilde and properly contains MRX. Okay, and now one can conclude therefore that any minimal prime of any prime here has to map to MRX. You can't have three things in a row. So any prime ideal, therefore it will be MRX and then Q. That's all. Therefore height of Q is equal to 1. Somewhere here we have assumed that Q is not MRX. Let's check that. Yeah. If Q is not MRX. Okay. If Q is MRX, then it is height 0. That we already checked. Okay. So this proves the base case. Dimension is 0. Okay. So now let's assume that dimension of R is positive. So now let dimension of R be n positive. Okay. Take a system of parameters. So, I mean, and this is just one could have done using Course principal idea theorem, but it's equivalent to saying that by of that dimension there is a system of parameters. Let's write sorry, not X, just to avoid confusion. Let's call them R1 through Rn, system of parameters inside M. Okay, then write R bar as R mod R1. Okay, we know that dimension of R bar is dimension of R minus 1. Okay, and write Q bar for the image of Q in R bar X. Okay. Q contains R1 because Q contains M, which is which contains R1. Okay. Okay. Yeah. Okay. So therefore, height of Q bar is less than equal to n. That's because Q bar. So this is equal to dimension of R bar plus 1. This is the induction statement. Height of Q is less than or equal to dimension R plus 1, which is what we wanted to prove. So we can assume this for R bar and Q bar. Height of Q bar equals dimension of R bar plus 1. Okay. which implies that q bar is minimal. So this is where we are using Krull's theorems, minimal over some S2 through Sn inside q bar. Okay, it is a prime ideal of height at most n, at most n. So S2 through Sn plus 1, let's call it. Okay, so it is minimal. So these are n plus 1 elements. These are n elements. Okay, so q bar is minimal over, sorry, that is some n elements inside q bar. Okay, this was a characterization of height. So now this implies now that q is minimal over R1, S2 and Sn plus 1. Okay. This is inside q. This ideal is inside q because R1 is in M. So when we kill that, we killed something inside q. So this now implies that height of q is less than or equal to n plus 1, which is what we wanted to prove. Okay. So now we have established the theorem, which we mentioned at the beginning, okay, and hence also the corollary. Okay. So let's quickly look at one more statement about finite type algebra over fields. Okay. So now at least we can go back to Noether normalization. Okay. So if you go back to Noether normalization, okay, so we have R finite type algebra over a field K, then there exists Z1 through ZD inside R, algebraically independent over K, such that R over this algebra, since they are algebraically independent, it's a d-dimensional polynomial ring. Now that we have established that there are d of them, the Krull dimension is d, okay, is finite. R over this is finite. Okay, so this is what we had proved. Okay, so and from this we had also, by looking at integral extensions, we had known that dimension of R equals d, dimension of this polynomial ring. Okay, so this was the d that came in the proof. Okay, so dimension of R is some integer, and as many as whatever that integer d is, that is the that's exactly the largest number of algebraically independent elements that one can find inside inside R. Okay, okay, and then at that point it is finite. So in this context we can prove the following proposition. Suppose that R is finite type over a field K, meaning finitely generated as an algebra over a field K. Assume that R is a domain. Okay. Then dimension of R is the transcendence degree of the field of fractions of R. So okay, over little k. This is okay, where QR is the field of fractions. To talk about the field of fractions, one has to be in a domain. So okay, the proof is just proof. Let d be equal to the dimension of R, then there exists Z1 through ZD inside R, algebraically independent over K, such that the polynomial ring generated by these algebraically independent elements sitting inside R is finite. Okay. So now let's take the field of fractions here. So let's call this ring A. Let's take the field of fractions A inside here, which means we inverted every non-zero polynomial in this. Well, this thing to here, whatever we get. Okay, so let's just, for now, let's just write A minus 0 inverse R. So to go from A to QA, we just invert all non-zero elements of A. Okay. But the property of being finite or the property of being integral is preserved under localization. So this is finite. So this is also finite. Okay. This is a domain, and we already saw that if you have a domain containing a field over which it is finite, then this is also, so this implies that is a field. This is a domain. That's R was a domain, and we just inverted some non-zero elements of R, and so this is a field. And then one can check that it has to be the fraction field, because R to this field there must be a map, and it must be same as a fraction field. It is first of all smaller than the fraction field, because we didn't invert, in theory we didn't invert all the non-zero elements of R, we only inverted those of A. But it must have inverted everything because this is already a field. Okay, so check that. Check that. If you invert all non-zero elements inside A, this is the fraction field. Okay, so this is the end of this proof. So in the next few lectures, we will concentrate on homogeneous ideals over polynomial rings over fields, because they are more amenable to computations. There are a lot of things to learn from that. And then we will maybe a lecture or so more about generalities about polynomial rings over fields, a property called a catenary, which we will do without proofs, because there's more theorems to be proved to prove that statement, and okay, we will not attempt that. At least we will become familiar with the notion even without a proof. And then in the final 8 to 10 lectures will be on homological algebra. What else can we use these computational techniques to, what else can we learn about these things?